Um, I
So,
guess no need for introduction, I guess. So let's just keep going. So here's a quick overview of what we're going to be going over today, or what I have presented. So inspiration, materials and methods, progression, future plans, and of course acknowledgments of who's helped me get to this point on my journey. So um, what I wanted to talk about first before even diving into serial diluters is what exactly is microfluidics. And you might have heard the term lab on a chip um, in chemistry or biology, but essentially it's small amounts of fluids to on a microfluidic chip, which you can see here, small channels. And the biggest pro about microfluidics is it's able to run faster reactions and cheaper because you use way less reagents than a traditional experiment. So that is like the biggest plus, the speed of the reaction and the cheapness. And some microfluidic devices that you could probably think about nowadays is like a pregnancy test, something who uses capillary actions where you only need small amount of fluids to get a result. So the next slide, oops. And but just because there's those two pros, price and speed of the reaction, there are some problems with microfluidics. One being the software. On the left hand side, you can see that we have NI which the annual cost to purchase or use the software is around $2,500. And on the right, you can see we have some solenoid valves and we have a PC. And the problem is, that's just more money. A good PC is about $1,000, and solenoids run you about $15 to $20 a pop, which is, sometimes you use up to 8, 12 of these solenoids. So all of a sudden you're in $4,000 just to run your experiment. And so those are some of the cons that come with microfluidics. And before I even dive into my other main core of this presentation, I wanted to talk about the inspiration and how we even came to the pneumatic serial diluter. I hope if you guys are not familiar with it, I will explain it. But there's this thing, a device called player pianos. You might have seen them at Disneyland or old Western films. And essentially what they are is they're player pianos are able to play by themselves. And this is before any sort of like technology was invented. These are ran purely on air with some bellows and some scroll sheets and some actuators and bellows. And you can see here's like the piano on the left-hand side. And you can see in the middle of the piano on the top, there's the small glass square. That's where you insert the scroll sheet, the paper roll. And I have a small video ready to play. It's only about 10-15 seconds, just to see what I'm talking about for these player pianos. Oops.
What is now a 100-year-old technology, which will hopefully bring to an even wider audience all of these roles.
I want my students to experience, to sort of taste the way this music felt and sounded. It's such a different way of playing than we're accustomed to. The conceptions of even of orchestration were very different, very colorful, very surprising. This is a gold mine.
So I just want you guys to keep in mind as you saw the paper wheels or the paper roll scroll over. And essentially what happens with the player piano is every time it hits a slit or one of the punch outs, it causes vacuum to be lost. The seal is done. But when the sheet covers the hole, it strikes a key. And that's essentially how it works. So the hole is covered, the key is struck in. If there's no hole, there's no keys that are played. And so that's how this piano is able to play by itself. And so going deeper into like the materials that were made this project even possible is I have to talk about these amazing materials such as PDMS, the laser color acrylic. So for my chip, we always use PDMS. And PDMS is a very porous material, really inexpensive, and it allows a bond to be put between the two acrylics. And then You see here, we have the laser cutter and the desktop CNC mill. It's more of a preference of choice of how you want to mill out the features that you will see shortly on my chip. And then the convection oven is to help anneal the chip. So which is pretty much help it bond to make it more pliable and then help get rid of some of the air bubbles. And then the corona treatment is a plasma laser, which helps, helps the bond be ensured and that the layers are adhering to each other. Oops. And so this is just the method how we assemble the chip. So we have our pneumatic little sandwich over here. So you can see that we have the glass slides which go over it, plastic bonding, the chip and PD mass, and it's all squished together with some binds. And then on the bottom, you can see here that it is in the convection oven. And I just wanted to play or as you saw playing on the right-hand side, this is the plasma laser treating our acrylic, which I think is super cool. I mean, who doesn't like purple lasers? So I wanted to throw this one here to give some other visualization. And then, so the valves. So this is kind of like the guts and glory of how this is all possible, to be honest, because these are some membrane valves and they pretty much act as pneumatic logic or gates. They allow gases or fluids to pass through. And you can see here on the right-hand side, we have a cross-section of it. So you can see the closed valve and atmospheric pressure. And that thin layer, the dark gray in between, that's the PDMS. And then, so when we apply vacuum, you can see that the PDMS is pulled into the valve, causing an opening to happen to allow the passing of air and fluids to pass through. So that's why these are so powerful and so useful, because it's a small, feature that has such a huge impact on our overall chips that allow us to run these kind of reactions and experiments. And so here is some previous work done by Dr. Pagel, and this is the foundation of my project too. And so you can see here, it looks a little, arbitrary or a little weird, but I'm gonna help break it down. So on the top right-hand side, you can see the fluorescent dye. And you can see as you progress down the slides 1 through 8, it gets dimmer and dimmer. And this is a serial dilution occurring in the pneumatic, in the microfluidic chip. So you can see it starts off very vibrant, very white. And by slide 8, it's very dim. This is approximately a 1 to 4 dilution. And we could easily run this again to have a 1 through 16 dilution. And on the left-hand side, this is an overview of the chip itself. And you can see here RO and RI, which means reagent in, reagent out. And then we have A, B, and C. And A, B, and C is the direction of the mix, and you'll see it very shortly. And the reason why I'm proposing a project like this too is because, many of us are familiar with serial dilutions, and they could be very time consuming, and they're very easy to mess up. And so this kind of takes out the guesswork for a very cheap price. Oops. So here we go. We finally made it to my current design. So on the left hand, you can see that I have this serial diluter with a punch paper program. And this is what I mean by when using the CNC mill or the laser cutter to etch out the features. You can see the little ring in the center with the small valves running out. And so this is all done by the laser cutter. These are engraved on these acrylic chips, and they're beautifully done. And, very proud of, what we've been able to accomplish in the lab, and very excited moving forward of what we can do. And on the left-hand side or right-hand side, I have a demo of the fluid pumping from the reagent in or the inlet to the outlet. And I want you to pay very close attention to the blue little orb or fluid buildup on the top left-hand side. And I'm just using my hands to pump it across instead of the punch paper, just for a better demo. And this video is sped up by 3 to 4x. And yeah, you can clearly see that the fluid is being transported over just for a proof of concept. So future-wise, we plan to have the paper scroll over instead of my fingers. Sorry about that. So future improvements of where we want to head with our device in our lab is on the left-hand side. I hope you remember the scroll sheet I was showing for the player piano, and we want to do something very similar. We want to be able to just place a sheet over the chip and then have it just automated roll around or scroll over the vents. So instead of having keys on piano actuate, we're going to have those valves actuate. And that's kind of, where we want to end up with this project. And on the right hand side, I know it might look a little weird with the gloss paper just kind of poking out right there, but the reason why we want to use gloss paper is, one, because it seals better due to being treated and not as porous as the paper. And two, we believe that we could couple this with the laser cutter and have our punch design as shown on the previous slide. So we want to have the gloss paper instead of there. And we believe with the laser cutter, again, that we could have these cuts out onto the gloss paper, and they will be a lot cleaner, a lot nicer. And finally, with the laser cutter and this gloss paper, we hope to just simply have it become a very easy process for future users. So they could just pick a design that they want and then just insert it into a laser cutter, or even just print it out and cut it with an X-Acto knife, and it's just good to go. And I just want to have some acknowledgement for everyone who's helped with my journey. So we have Dr. Grover, Dr. Huang, Dr. Bakta, Dr. Hui, Dr. Pavel, and then some of the PhD students, Samantha Robinson, and some of the and Raymond Yu, and some of the undergrads, Zanal Patel, Lee Chan. And then I am part of the transfer transition program here at UCR, and I owe a lot of thanks to this program. And thank you.